So we'll get started. So this is the session on blockchains. So welcome to the session on blockchains. So we have a bunch of interesting talks in this session. So we have our first presentation will be on a work that marries traditional databases with blockchain. The second work would be on exploring how we can use computation verification in the setting of blockchain. And then finally, we have another work that explores how we can use enclaves to kind of achieve better performance and confidentiality in the context of blockchains. So the first speaker is going to be Professor Carsten Bernig from Technical University of Darmstadt. He's also an adjunct professor at Brown University. And before that, he was an architect at SAP HANA. And he's a recipient of Google Faculty Award, and he has a bunch of best paper awards at IEEE, Big Data, and VLDB and SIGMOD. And he's been recently exploring the overlap between blockchains and databases, and he's going to talk about that.
Wonderful. Good. Do you hear me? So the mic should be on. So today, as Arvind mentioned, I'm talking about a database view on blockchains. So my main research is actually in general in distributed databases, especially distributed databases together with networks. So I'm a database person. Just to give you a quick introduction where I come from. So why I got interested in blockchains is because people are not using blockchains for cryptocurrencies only, but they use blockchains more and more for as general shared databases to write data into from one trusted domain and access it from another trusted domain. And the main reason why people are using it as a platform for data sharing is there are many different reasons. And one is because it keeps the history of all transactions, meaning if something is wrong in your database, you can go back and still look at what went wrong. And in some states in the US, they even changed the laws that the blockchains or the data in blockchain counts as evidence in court. So which is a strong reason if you share data between different trusted domains. The second one is why it's interesting is also because no tampering is possible after the fact. So once the transaction is in, you cannot modify the list of transactions you stored in your blockchain. And even more interesting, you don't need a trusted authority for making all these decisions. So the machinery in blockchain is designed in order to give you the two properties that it stores all transactions, and it doesn't allow tampering without having a trusted authority. So. And you see that it's actually used as shared databases, and there are many applications outside that try actually to use blockchains already as a shared database. And they range from different or cover different domains, not data just from health institutions, but also supply chains where you have different entities, a supplier and a manufacturer requiring to access the same database, but also to other use cases where you want to have decentralized copyright management. So for example, Bind it is a copyright management platform for images where you put in the image, it gets a timestamp, and thus it has the copyright. And if somebody else at the end wants to upload another similar image, you have the proof that the other image was in the database before. So the question is now, are we done now? Is this the end of the talk? So are existing blockchain systems as they are good enough for supporting all the different applications that people have in mind and when they want to use them as a shared database? So what I'm going to do in the talk is therefore, I'm first going quickly, I think most of the people might know the blockchain basics, but I still go quickly over the blockchain background, some basic terms that I'm not talking about things that are out of context in the rest of the talk. Then talk about the challenges, why blockchains, in my eyes, are not sufficient yet to use them as a shared database. And then go towards what we've been doing in the past year with BlockchainDB, developing a shared or database system on top of blockchains that mitigates some of the problems that we've seen or that I'm going to discuss before. Okay, so for blockchains, just the quick overview. I don't want to spend too much time. So blockchains at the basis, they use a tamper-proof ledger to store data, which I already mentioned. It's a list of transactions. It's append only. The transactions are appended in blocks. So if new data is written, the new data is appended or mined in blocks, and the ledger is fully replicated. And here you see already if something is mined or appended in blocks and it's fully replicated, there seems to be a lot of inefficiency in the system itself. And this is, again, one of the challenges that you tackle when you want to use it as a general purpose database system. So for why it's so interesting as a shared database, I already mentioned, is if an update happened to the shared database, which is replicated to all the peers in a blockchain, then everybody, or at least the majority, depending on what protocol you're using, needs to agree on the appends. And there are different ways to assure that. Never mind what you are using, if you're using a public or private blockchain, if that's what I'm also what we'll go over in a few seconds. And the last bit of piece of information that I'd like to introduce is the term of smart contracts, which are nothing else than trusted procedures that are stored in the blockchain that can modify data. It's your custom logic that you deploy in a blockchain. For a database person, it would be something like a stored procedure that can be called from outside. But for smart contracts, the specific thing is that all the participants agree on the same code if you run that logic. A second slide, just just to get the background right. So there are two platforms or ways how blockchains are deployed. There are public blockchains, means that every participant can join the blockchain, and they usually use more expensive consensus protocols. I don't go into details for those, but just to make sure that we are on the same side, there are also private blockchains which target a different type of application where not everybody is allowed to join the blockchain, but it's more limited set of targeted towards a limited set of participants that know each other, and therefore they use a bit of less expensive consensus protocols, and this already increases the performance a bit when you use blockchains as a database system. So the question is that where I'd actually like to start my talk: what are the challenges if you want to use a blockchain or blockchains as a shared database system? And the main challenge, I already mentioned, that is clearly the performance of blockchains. And there was a paper last year in SIGMOD where they analyzed the throughput and the latency of different blockchain systems. One is Ethereum, that is pretty well known, which you can set up as a public but also as a private blockchain, as well as Hyperledger, which is the IBM version of a blockchain system. But what you see here is that the throughput, for example, for a classical database benchmark, so if you use the blockchain just as a key value store, is pretty low. So they reported around, for Ethereum, around 300 transactions per second that can be executed. And if you look carefully in the paper, this is not the average transaction rate, that's the peak transaction rate. So the average transaction rate is actually much, much lower. And so clearly here you see that the transaction and the performance that you get, the transaction rate, the throughput and the latency that you get out of these blockchains is far from what typical applications need today. Even if, for example, if you look at what Visa is processing on average, so Visa transactions are around 2,000 transactions per second. And if you look into the applications, how people want to use blockchains, they also want to store sensor data in the blockchain, which even require much higher transaction rates. So the performance itself is one problem. The second one is if you today want to use one of the blockchain systems to set up a shared database, you are confronted with a slew of those systems, and it's really not clear which one to use. They come with different programming and execution models, and the question is which one is able to at least with which platform are you able to implement your logic that you want to have for the shared database? Where can you implement? In which can you implement transactions or the transaction logic that is needed for your use case? And even worse, because there's so much development going on, you don't know what is the best blockchain for your workload, and which ones will survive at the end, because there's so much movement in this sector, and people are trying to come up with optimizations, new platforms, and it's unclear which one you should build your shared database application on. The last one is even more severe, that blockchains, you might assume if you deploy your code in the blockchain, and run it, you get some kind, because even procedures run through the consensus mechanism that multiple nodes need to execute the same code bases, and at the end, the output of the procedure is verified, so meaning if all the outputs are equal. But that's not true for purely read-only functions that you would implement in your smart contract. They are only executed by one peer in the blockchain, meaning if that one peer, if that one node is malicious and you are asking or you're sending a read request to that one peer, you might get just a wrong value from the peer. And so the guarantees you're getting are for reads, for example, is not enough for many of the shared databases where you want to know, is the value I've been reading actually the value that is stored in the database? So there are many guarantees that you actually then want to add to your database system or to your, if you use your blockchain as a shared database. And what we think would be nice is if you could execute transactions on a shared blockchain at the end, verify if the execution of the transaction, meaning of all your read and write operations, was correct with regard to the guarantees what the database wants to give you. And if you discover that a violation happened, that you can go back to the last verified checkpoint. So the ideas of transactional theory more implemented in blockchains, but also transactions that are verifiable. So how are we going to achieve this? And this is the idea of blockchain DB. The idea is that we build a middleware on top of blockchains. The idea is what the blockchain DB gives us is that it gives us a unified API. So we tackled the problem of having a zoo of those systems by having a unified front end and exchangeable back end, similar to what MySQL is today for databases. You get a unified front end. You can plug in your storage engine that you like to have, and which gives you the performance characteristics maybe that you want to have for your application. The second one is that we can apply typical database optimizations in the middleware. So we've seen that the performance itself is a major limitation, and by applying some tricks in the middleware, by sharding across certain blockchains, we can achieve much higher throughput than what the existing blockchains give us already. And the last one is that we want to support this notion of verifiable transactions. So executing read-write operations via the blockchain DB, and then at the end getting the verification mechanism that tells us is that the operation or is the transaction that we've executed been correct with regard to the consistency level, for example, selected in the database system. Now you could argue, okay, blockchain DB, this is a component that runs outside of your blockchain, so it's an untrusted component. Doesn't it make things harder? I'll come to that at the end, and where I talk a bit about how we deal with verification with a new component that is actually untrusted. So what we've actually been building in the last year is not a full database system, but as a first step, we've started to build a middleware that has a simple put-get interface, because this is already from as a basic building block we think we can use later on to build transactions on top. And B, it gives us already proof of concept, how far can we get with transaction rates if we have just a simple put-get workload. So the idea is we have a blockchain key value store that supports at the beginning only the simple put-get operations that we have here, and we have pluggable backends. Inside the blockchain, in order to achieve the higher performance and implement some database optimizations, we selected a bunch of techniques that are implemented in the middleware, be it from sharding the data into multiple blockchains, so not using just one. This is a thing that already some of the blockchains do by now inside the blockchain system. They support sharding, but not all of the systems support it. So what we can do is just put that on top and support. That way, some data parallel execution across blockchains, because if you look a bit deeper into the execution models of blockchains, they are typically fully serialized execution with no parallel execution of transactions at all. And the sharding gives us some way of parallelizing. And we implemented a bunch of other optimizations, and I want to go just in two of them and show you quickly what the performance impacts are if you do that, or if you implement those in the middleware. The first one is, so the question is, if you provide a put-get interface, so what consistency can we provide if we use a blockchain? And in blockchain key value store, we support different notions of consistency levels or client-side consistency levels. that are more expensive or less expensive. And the idea is that if we give up some of the consistency similar to what normal databases also do, we can get higher performance even when we use a blockchain as a backend. And the idea here is that if you use a higher consistency level, for example, read your own writes, what we do in the middleware, if a write is coming in, if a put is coming in, it's first submitted to the blockchain, but we don't wait for the commit or that the transaction is actually committed, but only that it's validated. And after that, we just append it to a list in our middleware, meaning that once a read is coming in for the same key, at that moment we do lazy blocking on the pending transaction and wait for the transaction to be committed before we give back the value. So this is one technique where you already don't need to wait for the full execution of a transaction, but you still get a guaranteed consistency level, which many of the applications desire. Or you can even go lower and provide only eventual consistency and even don't wait for the transaction to be committed and execute just read operations completely on the status you're getting and monitor if these transactions finally commit, so if you can still guarantee liveliness. And what you see here is that if you implement just on using a 50-50 workload, so 50 reads, 50% writes, and Ethereum as a backend, if you want to provide read your own writes semantics, you get only a throughput of 20 put-get operations at a second. And this is in line with the Blockbench numbers. If you look a bit closer, they reported only numbers, as I said, for max throughput and not for average throughput. See, the eventual consistency gives you already a boost of a factor of 5 in terms of transactions, which is still not there what many of the application needs, but it's already a way of getting higher performance out of your blockchain system if you decrease the consistency level. A second technique that actually is helping much more is that in our middleware we implemented some form of batching, so we don't submit puts one by one to the blockchain because the per transaction overhead of validating transactions is pretty high. So meaning if we batch them together, so multiple puts in one blockchain transaction, you can get, for example, if you block up to 500 puts in one call, a transaction rate of 1,200 transactions per second. After that, the message size or the maximum message size we used here, 4-byte integers, is exceeded. So there's a limit of batching that you can use. So the playing database tricks is one thing. But the question is now, I mentioned a third point, which is important, that is getting verifiability of your operations. And this is something that we also implemented inside blockchain inside our system. And the problem here is, or the idea of verifiable consistency is that a client can verify the correctness of all operations, meaning if the puts and gets that he executed and that he sees or that he executed adhere to the selected consistency level. So what does it mean for eventual consistency? It means for eventual consistency that a client doesn't see any fake reads. So if you think about a scenario where, for example, the blockchain middleware or one of the peers is malicious, he might return just a value that is not stored in your database, and we want to be able to detect it after the fact. And if you use a blockchain system out of the box, you don't get that guarantee. And the second one is that we want to, for example, or in eventual consistency, we also want to support liveliness. So we want to assure that all the puts that are executed through blockchain key are actually stored in the blockchain system and not dropped again by one of the components. So the problem is that, as I mentioned, that all these operations, all these guarantees could be violated because in our setup, we have multiple untrusted components. One is our blockchain key value store that we are introduced as a middleware, but there's also the peers themselves, if you look at them individually, are untrusted. Meaning, if we just go to one of the peers, we might get the problem of fake reads, and reads are actually executed by only one peer. So it's a problem of detecting if you get a fake read, or if, for example, the blockchain middleware or the peer drops a transaction and doesn't execute it. how we do it is, so here just a high-level overview is the idea is that we use deferred verification mechanism where every put that is executed through the key value store updates the write set in the blockchain itself, and the clients additionally lock their actions, their read and write set. They don't need to do it for each individual call, but they lock their read and write set, not using the middleware layer, but going or bypassing the middleware. They lock their reads and write sets into the blockchain as well. The nice point about these calls is they don't need to be synchronous blocking. You can just send them asynchronously. And at the end of your epoch, when you executed multiple of the puts and gets, what you want to do is also a verification procedure that looks into the question if the write set was included, that the clients reported via their record calls is included in the write set that the key value store was seeing. And this is also, again, a non-blocking operation, means we submit that as a blockchain transaction, so implemented as a stored procedure, as a smart contract, which checks if these two guarantees are satisfied. And once it's done, we can just fetch the result if the epoch was correct, if all the operations have been correct. And in worst case, roll back in the transaction history to a point where where the last verified epoch was stored in the database. So we can also recover to valid checkpoints. Good. So there's many more details you need to think about if you want to do verification with the blockchain, and there are more details I haven't been including in the slides, but this is the general notion of how we want to ensure that puts and gets are executed correctly. So what are we up to next? So we just, as I said, it's the first step that we implemented. There are many more optimizations that we haven't implemented, for example, caching in the middleware, but still guaranteeing verifiability. That's something we are working on at the moment. And then for sure go in the route of having not just a put-get interface, but supporting full database transactions on top of our key value store interface. So in long term, what we want to achieve, or how we think that our middleware could be integrated into a data management stack, is also have a combination of a database that is running on-premise, where you use the blockchain database system to integrate something like a shared column into your database, into your local database system. Meaning you create a table, you mark your column as shared, and by getting the guarantees of verifiable transactions and sharing on those columns, so data is automatically written to the blockchain, and you can verify for those columns if transactions on those columns have been right. But this is something we haven't started thinking about in detail. With that, I'm at the end of the talk. Happy to take questions. I'm not sure if we have time for questions at all.
We can do a couple.
Good. Yeah.
So you cited a Sigma paper saying that even if you set up a private environment to run blockchain, and the throughput is very limited, right?
Yeah.
So I just intuitively have a hard time to understand why that's the case. I wonder if we can share some insight.
You mean why the transaction rate of blockchains? So depending. So I haven't been going into the details of the execution models of blockchains. But for example, public blockchains use so consensus protocol, which is called proof of work, meaning. That one was private, yeah. And for them, as I said, so the complete transaction. So for private for private blockchains, the problem is that the execution of all transactions is fully serialized, meaning one node takes a set of transactions, executes them, distributes the results to all the peers in the blockchain, and they re-execute the transactions to verify the outcome of the transactions. And then if the results are, if different peers agrees, or different peers or the majority agrees, the block is appended, which is inherently so a full replicated database system that doesn't allow any concurrency. And the results that you are seeing is, and there are many more overheads in blockchains, which is not just the execution, but also verifying the signatures for each and every transactions, etc. Yeah, Mike.
Okay.
Mike, yeah.
Mike with the mic. I was just curious if you could give us a feel. I know you didn't go into the details of the blockchain protocols, but is there something fundamentally different with using blockchain as the back end for the key value store as opposed to if you were just building a federated database over a bunch of slow database systems where you would be faced with a lot of the same challenges?
There are two answers from my side to your question. The first one is, so why not using, or why don't you use a database system or more a replicated database system from the start for those use cases? And yeah, but that's a valid question. And so the answer is here. So for me, people are using blockchains nowadays, and and it has this legal notion that data that is stored in a blockchain can be used as evidence for court. So there are already some mechanisms in place that you don't have for databases. So there are reasons why people should use a blockchain. So therefore, it's for some use cases even not possible to start with a database system as a starting point. The second one is regarding the performance. I think that we saw already the talk, for example, from Microsoft in the morning. There's a lot going on in optimizing the performance of blockchain systems themselves, and we just benefit from it. So whatever comes next as a platform, we can plug it in as a backend and use it and provide the verification guarantees on top. And this is what let's say the value of what we provide is. So you get the interface of a typical database. You can verify your transactions, your put-get operations as if it would be a database, but at the end it's a blockchain. So we provide a stable interface. You can program against it from your application and get the advantages from new blockchain systems.
Assume we move from proof of work to proof of stake, and assume every block can pack 10,000 transactions. What would you imagine will be the next bottleneck in terms of improving the performance of blockchain transaction processing?
So we haven't been ourselves not looking too much into where the bottlenecks of current systems are. There are two good papers about that analyze actually the performance bottlenecks and where are the limits of how far could we push the performance if we tweak the parameters. There's one from a bunch of authors from ETH, Cornell, etc., where they theoretically analyze where's the upper bound with the current protocols. I think that's a nice read. Anyway, so and the second one is Blockbench, where they were running already some against different systems with different consensus protocols workloads. From my perspective, so what I think blockchains should do is, so the computational or the execution of transactions is inherently inefficient, as I said. It's completely sequentialized. There's no notion of concurrency, and I think blockchains can learn a lot from what databases have been doing in concurrency, so executing transactions as if they would be serialized, if they would be serial, but having actually a concurrent execution. And if we can get some ideas of those into the next generation of blockchain systems, it would increase the performance and reduce the bottleneck of what current blockchains have.
All right, I think we are like running slightly behind schedule. So if you have further questions, we might want to do it in the break. So we'll thank the speaker.
Yeah, thanks.
So the next speaker in this session is Srinath. So Srinath is a researcher at Microsoft Research at the Redmond Labs, and Srinath is an expert on building systems around like verifying of computation, around computation verification. And in this talk, he's going to talk about a system called SPICE, which is about verifiable state machine, and this work is going to appear at OSDI this year.
Can you hear me? I think it's working. Okay, thanks, Arvind. So this talk is about a powerful primitive called verifiable state machines and a system that implements this primitive called SPICE. This primitive has many applications in the context of trustworthy cloud services as well as decentralized blockchains. I'll start by defining what this primitive is. A verifiable state machine is a primitive in which there are three types of entities: a set of clients, a stateful service, and a set of verifiers. These clients issue a set of requests to the service and get back a set of responses. Then the service periodically publishes a trace which contains an entry for each request-response pair. Then each of these verifiers run a set of local checks and then output accept or reject. And then we call such a primitive as a verifiable state machine if it satisfies these properties. First, if the service behaves, that is, the execution is equivalent to some serial execution of the concurrent request, then the verifiers output accept. Second, if the service misbehaves with the execution of a request or with concurrency control mechanisms, then the probability that a verifier outputs accept should be less than epsilon, where epsilon is very small. Third, the trace itself is zero knowledge. That is, it does not reveal anything about the requests or the responses or the internal state of the service beyond the validity of the correct request execution. Finally, we require each entry in this trace to be small, for example, a few hundred bytes. It turns out there's a lot of prior work that implicitly implements this verifiable state machine abstraction. They do not use the state machine formalism, but it's not fundamental. The theory actually dates back to early 90s, but this theory was too expensive to be implemented. However, there's a lot of work that reduces the cost of this theory by over 20 orders of magnitude. And these latter systems add support for stateful computations in those earlier systems. For example, they support storage interfaces such as key value stores and even a limited form of SQL databases. Despite this massive progress, all of these systems have two key limitations. First, the storage operations in these systems are very expensive. For example, it would take tens of seconds or even several minutes for each storage operation. Second limitation is that they only support a sequential model of execution for expressing these services. As a result of these two limitations, prior work can only support very limited throughput even for very simple services. Our system, which is called SPICE, addresses these limitations. First, it features a new storage primitive that is 2 orders of magnitude more efficient than prior instantiations. Second, it supports a concurrent model of execution for expressing services. As a result of these two new techniques, SPICE can support thousands of transactions per second for many realistic applications. In the rest of this talk, I'm going to focus on 3 things. First, I'll discuss a few applications that can be built with verifiable state machines. Second, I'll present some background on prior work and a quick overview of SPICE. Finally, I'll present some experimental results. At a very high level, we are interested in this primitive verifiable state machines for 2 reasons. First, it enables us to build cloud services in which we do not have to trust the cloud infrastructure. Second, it also enables private and efficient blockchains both in the permission membership model and permissionless membership model. I'll start with the first application scenario. The first application is a cloud-hosted ledger inspired by Sequence. Here, the service maintains balances of assets owned by different clients, and it exposes 3 types of requests. First, the issue operation enables an issuer, which is a special entity in the system, to issue some assets to a client. The second operation is a transfer that allows one client to transfer an asset to a different client. Finally, the last operation, which is called retire, allows a client to take an asset out of the system. So in the status quo, if somebody wants to verify the correct execution of this service, they have to get a complete trace of all the requests, responses, and the internal state of the service. But with SPICE, an auditor can verify the correct execution of the service without access to any of the requests or the responses. And it does not have to trust the infrastructure on which the service is running. The second application is in the context of decentralized blockchains such as Ethereum. On Ethereum, a smart contract is essentially a state machine where two or more counterparties can issue transactions to create state transitions. So in the status quo, all the transactions are actually stored on the blockchain. So this provides no confidentiality guarantees. Anyone in the world can inspect the internal state of the contract and also look at all the state transitions a contract has gone through. Second, every request from the app must be processed by the blockchain. So this limits the application level throughput that you can get by storing a smart contract on a public blockchain. Whereas with verifiable state machines, you don't actually have to execute those smart contracts on the blockchain. You can execute them outside the blockchain and then persist only a succinct zero-knowledge trace on the blockchain. Because this succinct trace does not reveal anything about the internal state or the requests or the responses, it provides very strong confidentiality guarantees. And because Ethereum will only process a succinct trace, you can actually support very high throughput for your applications, which is independent of the throughput supported by Ethereum. So I hope that I convinced you that verifiable state machines are actually useful. So in the next part of this talk, I'm going to provide some background on a prior system called Pantry before I provide an overview of SPICE. So Pantry itself extends two prior systems called Zatar and Pinocchio to support a notion of state. All these three systems are composed of a front end and a back end. This front end translates a C program into a set of algebraic constraints, and then the back end implements an argument protocol to prove the correct execution of this C program. I'm not going to go into the details of how these components work, but I'll just observe that both Zatar and Pinocchio support a large subset of C. This in turn enables verifying the execution of stateless programs. And then Pantry supports state while working in the same stateless computational model by leveraging cryptographic hashes. I'm going to briefly tell you how this is done. So the key idea in Pantry is to name data blocks using a short cryptographic digest of those data blocks. Here's a very small C program that illustrates this key idea in Pantry. It takes as input a digest, and then the prover or the service can actually supply state. Of course, because the service is untrusted, it can supply any state to this program. But there's an assert statement that checks if the digest supplied by the verifier equals the cryptographic hash of the block supplied by the service. And if the service supplies the correct state, this check passes, otherwise this check fails. And by using this idea, Pantry builds a key value store. The core idea is to treat hashes of data as pointers to such data. Then you can build a tree, and which in turn can be used to build a key value store. But the fundamental problem with this approach is that cost of a key value store operation is logarithmic in the size of the state. Concretely, this means it takes several minutes of CPU time, even with a million key value pairs in your state. SPICE addresses these performance problems. The core idea in SPICE is to use a set data structure instead of a tree data structure. We then map key value store operations to operations on a set. As a result, the cost of a storage operation is constant time instead of logarithmic on an amortized basis. However, if we instantiate this idea naively, it's actually going to be more expensive than the tree-based approach. Constants involved, and in the case of many data sizes that we are interested in. However, SPICE solves this problem. It does this by using an efficient instantiation of this set-based data structure using elliptic curve cryptography. SPICE also includes new techniques to execute these state transitions or transactions inexpensively in this model. I'm not going to go into the details of how all of this is done, but I'll just present a few implementation details and how the system looks. We implement SPICE on top of Pantry. We also wrote 3 applications using SPICE, but SPICE includes a toolchain using which you can build many more applications. The toolchain takes as input a C program, which expresses a request handler, and then it outputs 2 executables, one for the service and one for the verifier. And this request handler can include arbitrary C code, and it can also call into SPICE's storage APIs. The storage primitive itself exposes many APIs. First, it provides you operations on a key value store, such as get and put. Second, it allows mutual exclusion APIs such as lock and unlock, so you can lock a key, perform an update, and then unlock. It also provides a restricted form of transactions. So you can call begin transactions on a set of keys. It returns the current state of those keys. And then you can do arbitrary computation, and then you can call end transactions with the values that you want to write back. And all of this update happens atomically. In the next part of this talk, I'm going to present some experimental results. There are 2 questions that I'm interested in. First, how does SPICE compare with prior state-of-the-art? Second, what is the end-to-end performance of applications built with SPICE? To answer these questions, we run a set of experiments on an Azure cluster. So for the first question, we measure the throughput of key value store operations under SPICE, as well as a set of baseline systems. We preload the key value store with 1 million key value pairs, and then we measure the throughput of the system for get and put operations separately. As you can see, due to new techniques in SPICE, SPICE can achieve up to 4 orders of magnitude speed up compared to the baseline systems. So to answer the second question, we implemented 3 applications, and this graph depicts end-to-end performance with varying number of CPU cores. On the x-axis, you can see we have depicted various request types, such as issue, transfer, and retire, that are supported by these applications. As we can see, SPICE achieves a near linear speed up in throughput as we provide more CPU cores. I did not depict the verifier's throughput, but it's much more than the prover's throughput or the service's throughput, which is 15 million proof verifications per second on the same cluster. So to summarize this talk, we believe verifiable state machines is a key tool in the context of both cloud computing and decentralized blockchains. SPICE represents a substantial progress towards efficiently implementing verifiable state machines. Finally, we are excited about the many possibilities that this work points to. With that, I can take questions. Someone has a question.
I'm sorry, I kind of lost the connection between SPICE and a blockchain. So where exactly are you using SPICE as technology to implement blockchains, or is it a front end to blockchains? Because you're using a code generator, so I don't know exactly what the connection is.
So there are 2 applications that I guess I can go back. So I guess the application, the blockchain, here's the scenario that I presented in the context of blockchains. So instead of running the entire smart contract on the blockchain and then executing that contract on every node in the blockchain system, you could run it once and then you could just persist that sussing zero-knowledge trace on the blockchain. So the entire blockchain network would just verify that there was a valid state transition, and it does not have to re-execute any transactions, and they also don't need to know what the contract was or what this contract was doing. So it provides confidentiality and also scalability.
So you're basically like a front end to the blockchain.
Yes. So
You don't need to use a blockchain in the back end. You could put it in a database.
sure.
So
Yeah.
the fact that it's a blockchain is actually not relevant.
Yes. So here only the verifier is running in the blockchain, but you could run that verifier anywhere.
Right.
And even the service itself could be running outside the blockchain using traditional databases.
All right. Okay. Thank you.
The trace includes all the hashes of the state. Yes.
Can you return to the slide that gave the big picture of requests going into the blockchain and the trace going to the verifiers?
Is it this slide?
Yes. Could you say what information the verifiers have access to in order to make the decision? This picture depicts only an append-only trace. Are they aware of other information?
Yes, yes. They do know the specification of the service. For example, what it means for taking a state transition. So they know the code that represents the state transition. They also know some encoding of the request and the encoding of the responses. So this trace has an entry for each request-response pair.
So the verifiers are aware of something about the requests.
They don't know the actual request, plain text contents of the request, but they have a succinct encoding, which is a commitment to this request.
Thanks.
A quick question while we're on this slide. So you define soundness in terms of some epsilon. So what should I think of epsilon as being? Like the internet is very large and there are many requests. So,
Yes.
so how often in practice would you expect soundness to be violated?
Yeah. So this epsilon is 1 in 2 power 128. So you can think of it as 128-bit security. So it should be very small. Like you should absolutely not see verifier accepting some incorrect statement as correct, except with that 1 in 2 power 128. Which is the security of many crypto primitives that we use.
So the final presentation in the session is by Professor Dawn Song from UC Berkeley. So she has a whole bunch of awards. So she's a MacArthur Fellow, so she's a Guggenheim Fellow and MIT 3R35 Award. And she has like several best papers in security and learning conferences. And she also happens to be the co-founder of a startup in blockchain called Oasis Labs. And I believe that some of the work she'll be talking about is based on, is related to the startup as well.
Okay, great. Hello, hi everyone. Okay, great, so the mic is working. Okay, great, thanks a lot for being here. I'm Dawn Song. I'm a professor in computer science at UC Berkeley, and also I'm a founder and CEO of Oasis Labs. So today I'll talk about privacy-preserving smart contracts at scale, a new blockchain platform that we're building. Okay, so as we all know, data is the new oil, and all this data can really help us with the valuable data analytics and machine learning, and help us gain insights in many different domains, including healthcare, financial services, and IoT. However, a lot of data is also sensitive, and we are actually facing a lot of big problems in the data domain today. For example, data breaches are the commonplace now. For example, Equifax, one of the largest credit score companies, had recent data breaches where attackers were able to steal sensitive information about more than 140 million users. On the other hand, a lot of valuable data is also being siloed. Because the data is sensitive, they couldn't really be utilized, and hence a lot of data we are not being able to extract valuable insights from all this data, including, for example, medical data and financial data and so on. And also, at the same time, users are losing control of their data, as demonstrated in the recent Cambridge Analytica incident. So on the other hand, we are seeing that blockchain is providing a transformative technology aiming to solve a number of problems. Blockchain aims to provide openness and transparency and allow us to not rely on any central party and provides automatic enforcement of agreements. So far, what has blockchain brought us? It helps with payments, with ICOs, and CryptoKitties. So the question is, in the future, we hope that blockchain can do even greater things, can help us to revolutionize many different segments in industry, including, again, financial services, healthcare, IoT, and many, many other domains. So today I want to talk about some new technology that we have been developing that actually helps bring in the blockchain technology to a broader domain to enable these other more advanced applications than the ones that we have seen today. And also at the same time, help us solve some of these data security and privacy problems that I just mentioned at the beginning. So first, let me give you one motivating example how, in such an example, how blockchain can help solve the problem and also where we need new technologies in blockchain. So this motivating example is in the area of fraud detection. So for example, for banks, they need to do fraud detection to figure out whether they should give someone a loan or whether there are suspicious or malicious activities. So typically how it works is that each bank, using its information, can train its own fraud detector. And because the data is sensitive, and usually it's difficult for the different banks to collaborate together. However, as we all know, the effectiveness of these type of models it really depends on the amount of data that the model is trained on, or the broad views that the model actually has seen. And hence, it would have been really nice if we can develop a technology that allows these different banks to collaborate together and using the data from each of the banks together to develop a better machine learning model for fraud detector. And unfortunately today, we don't have a technology to enable the banks to do this because of privacy concerns, regulatory risks, and misaligned incentives. So this is an example where actually blockchain can help, and in particular, a new type of blockchain technology, such as the ones that we are developing, can help, where we can actually develop smart contract, in this case, a fraud detector smart contract that runs on top of the blockchain. And in this case, the different banks, each of them can actually contribute data to the smart contract. And together, using the data from these different sources, the fraud detector smart contract can train a fraud detection model. And hopefully this fraud detection model that's trained using data from different banks can be much more effective and can really help each bank to deal with fraud much better. However, in order to enable an application like this, we need to solve a number of challenges and issues. So first, in a typical blockchain, actually all data and compute on the blockchain is public. And in this case, we are dealing with very sensitive data, essentially users, customers' transactions. So we need to handle the challenge of having sensitive data on the blockchain worker nodes, essentially protecting the computation process of this smart contract execution from leaking sensitive information. And secondly, the computed fraud detection model itself can potentially leak sensitive information about the inputs because the machine learning model here that is trained is trained from sensitive inputs to start with. And I'll show a little bit later that our work has shown that even when you train a machine learning model, if you are not careful with the privacy protection, the trained machine learning model itself can actually leak sensitive information about the inputs. And finally, today's blockchain has huge scalability issues. Today's blockchain has poor performance and very high cost. So again, in order to enable an application like this, we really need to be able to scale up the blockchain scalability to enable real-world applications like this, and ideally at the cloud scale even.
Question.
Uh-huh.
So what about the smart contract or the fraud detection model? Isn't that private? Isn't that important too?
So that's why I'll talk about this. Yes, so we are actually going to develop a privacy-preserving smart contract that can help save all this. Mm-hmm. So in order to enable an application like this and address the challenges that I just mentioned, at Oasis we are developing a new blockchain technology called one of the key of our blockchain platform is privacy-preserving smart contracts at scale. So first, one of the key primitives of our platform is privacy-preserving smart contracts. And the privacy-preserving smart contract satisfies a number of unique properties and capabilities. It enables automatic enforcement of codified privacy requirements. So the privacy requirements here is coded into the smart contract. And we can enforce this without relying on any central party. And it's designed to scale to real-world applications, including heavy workloads such as machine learning. And we design the technology to make it easy to use and to make it much easier for developers to build privacy-preserving applications without needing to be a privacy expert. In order to enable this privacy-preserving smart contract at scale, we develop a number of different technologies and combine together to build our Oasis blockchain platform. The Oasis blockchain platform essentially you can view it as two main parts. There's the platform layer, and the platform component, and there's the application component, where the smart contract is the abstraction at the application level. So at the platform level, so first we build confidentiality-preserving smart contract execution to protect the smart contract execution process from leaking sensitive information about the inputs. And at the application level, within the smart contract, we provide capabilities for privacy-preserving analytics and machine learning to make it easy for developers to do analytics and machine learning without needing to worry about privacy and to enforce the desired privacy policies. And at the platform level, we also develop a new architecture for the blockchain to enable scalable smart contract execution, in particular for scalability for complex smart contract execution. So now let me talk about each component technology separately. So first, let me talk about the confidentiality preserving smart contract execution. So typically, again, as I mentioned, so most blockchain today, the data and compute are public on the blockchain, and hence they can only have very limited use cases. So in this case, the input to the smart contract is public, and the smart contracts essentially then takes the inputs, does a computation, and performs a state transition. And also the states of the smart contract in most of today's blockchain platform is also public. So when we do confidentiality preserving smart contract execution, essentially here, everything's encrypted. So the data is encrypted, and also the states is encrypted as well. And the smart contract essentially does a computation on encrypted data and to perform the state transition. And also, at the same time, we want to ensure that even though the data and states are encrypted, we still want to ensure that we can have a proof of correctness that the state transition is correct. So the question is how we actually enable this a practical way of doing computation over encrypted data, and in particular, this confidentiality preserving execution. So this essentially, we do this by leveraging a combination of different techniques for secure computation. So in secure computation, essentially, we have two main types of approaches. The first one is secure hardware. The advantage of secure hardware is that it's highly performant. Its performance is close to native computation, and it can support for general purpose computation. The challenge for the other types of approach is crypto-based techniques, such as secure multi-party computation and fully homomorphic encryption and so on. The challenge for this type of approach is that the performance overhead can be very high. Oftentimes, it's orders of magnitude higher than native computation, and hence it can only be used for very limited use cases. And in the Oasis blockchain platform, we actually use a combination of these different techniques. And depending on the actual use cases of the smart contracts, we use different combinations of these techniques to enable confidentiality preserving execution. So now let me just briefly say a few words about the secure hardware aspect. So the secure hardware here, one abstraction is called the trusted execution environment, and also here we call it the secure enclave. The idea of secure enclave is that here we can run a program, in this case, a smart contract, inside the secure enclave. And then in this case, the operating system and the application that runs outside of the secure enclave will not be able to tamper with what's running inside, and also will not be able to see what's running inside. And hence, the secure enclave helps provide integrity and confidentiality of the execution. And also, at the same time, the hardware provides a hardware-based mechanism for remote attestation, such that the remote verifier can remotely verify what has been run inside the secure enclave and its initial state. So we have developed a research project called Ekiden, leveraging approaches like this. And we provide security proof using universal composability. And we have developed a number of sample applications, including training machine learning models in healthcare domain and smart building domain and many other applications. So here, one of the key capabilities that we use to enable confidentiality preserving smart contract execution is leveraging the capability of secure enclaves. And in fact, the secure enclaves can and serve as a cornerstone security primitive even beyond the application domain of blockchains. Secure enclaves can provide strong security capabilities and can serve as a platform for building new security applications that couldn't be built otherwise for the same practical performance. And over the years, so all the hardware manufacturers have recognized the importance of building secure hardware, and they all have built different solutions. But however, we still have huge challenges in building secure hardware. For example, how secure can it be, and what's their models, and what would you entrust with the secure hardware? And the ultimate challenge is, can we actually create a truly trustworthy secure enclave as a cornerstone security primitive that can be widely deployed and enable secure systems to be built on top? If we can do this, then we can truly usher the whole community into a new secure computation era. So what's the path towards building trustworthy secure enclave? So first, we need to have an open source design. An open source design provides transparency that's needed for the whole community together to analyze and verify the security and correctness of the secure enclave, and can enable much higher assurance. And also, open source design helps build a community. And also, ideally, we would like to provide a formal verification of the secure enclave. And we want to ensure secure supply chain management for securing the manufacturing process. So towards this goal, we are doing a project called Keystone Enclave, aiming to build an open source secure enclave on top of RISC-V chip, which is an open source RISC architecture that's available today. And we provide strong memory isolation and many other properties with the goal to enable open source secure enclave that can really be deployed and be used and be manufactured by any manufacturer and be used in the real world. And RISC-V actually has been widely adopted in industry. The RISC-V Foundation has more than 100 members. And you can find out more information about Keystone at our website, keystone-enclave.org. And we have a number of goals in the project to help us to finally achieve the goal of building an open source secure enclave. And this is a collaboration between Berkeley and MIT and with other institutions joining. And we plan to have a first release this fall, both as deployed on FPGA, as well as actually on a demo chip on High5 Unleashed, the RISC-V chip. So that's the first component technology, confidentiality preserving smart contract execution. Let me then also quickly talk about the second component technology for privacy preserving analytics and machine learning. So when we do data analytics and machine learning, there is a lot of privacy risks. So for example, here, there are two types of questions. One is how many trips were taken in New York City last year. The other one is how many trips did Joe take last week. So as you can see, one question reflects a trend, and the other one actually leaks sensitive information about the individual. But to answer both type of queries, you actually both need to actually have access to data. And hence, this is an example showing that just having access control is insufficient to be able to protect privacy and at the same time being able to answer queries like this. And there has also been proposals using data anonymization technologies to solve this problem, but that's also insufficient. Data anonymization can reduce the utility of data, and also at the same time, it provides insufficient privacy protection. There has been lots of research showing that anonymized data sets, actually when it's combined with other publicly available data sets, can be used to re-identify users, and hence leaking sensitive information about individuals. We've also done the recent work showing that even when you train a deep learning model, you actually really need to be very, very careful. So the question here is, do neural networks actually remember training data? And if yes, can attackers actually extract secrets in the training data from just simply querying the learned models? So in collaboration with the researchers from Google, in our recent paper, here is an example of one of the case studies. We show that when we train a language model on the email data set, in this case it's a public Enron data set, the Enron email data set naturally contains credit card numbers and social security numbers of actual users. And we demonstrated that attackers can actually craft attacks to then, by just querying the language model, to be able to extract the credit card numbers and social security numbers from the original training data set. And this is an example demonstrating that even when you are training a machine learning model, you have to be really careful to take the correct measure to protect users' privacy. So luckily, here we actually have a good solution. So instead of training a vanilla deep learning model, instead, if we train a differentially private deep learning model, then in this case, both from our proposed measure as well as attack evaluation, we demonstrate that by training a differentially private deep learning model, we can provide much stronger privacy protection for the users. So I'm running out of time, so I won't have time to actually go into the details about differential privacy and so on. So differential privacy at a high level is essentially a formal privacy notion that helps to measure for an algorithm, either a data analytics algorithm or machine learning algorithm, whether it can distinguish whether a particular user's data has been used in producing the data analytics results or training the machine learning model. So differential privacy provides a very strong notion for protecting users' privacy in data analytics and machine learning. There has been very limited real-world use of differential privacy, including Google and Apple use differential privacy in very limited setting. And there's no previous real-world deployments of differential privacy for general-purpose analytics. And there are a number of challenges for deploying differential privacy in practice in the real world, including usability for non-experts, broad support for analytics queries and machine learning, and also easy integration with the existing data environments. There's no previous system that addresses all these issues. In collaboration with Uber, we have developed new systems to address these challenges. And in our system, Chorus and Upshill, we essentially developed techniques and tools to automatically rewrite data analytics and machine learning pipelines to enforce differential privacy and as well as other desired privacy requirements. And some of our technology has already been deployed at Uber for protecting privacy in their internal data analytics. So putting together confidentiality preserving smart contract execution and privacy preserving data analytics and machine learning, so this enables the privacy preserving smart contracts. And now let me just briefly talk about the third component technology, scalable smart contract execution. Again, I don't have a lot of time left, so let me just go over this very quickly. So typically when people talk about blockchain scalability, one thing that people immediately think about is blockchain sharding. It's like you have one lane of cars, but now you have many lanes in parallel to improve the throughput of the traffic. However, this type of approach is good for high throughput of simple transactions. But however, for the kind of blockchain applications that we want to build, these are often much more complex, and the different smart contracts can also depend on each other. So to enable scalability, in particular scalability for complex smart contract execution, we have designed and developed a different blockchain architecture than previous blockchain architectures. And in particular, by separating out execution from consensus, by decoupling the different functions that a blockchain is providing. So our design is inspired by a few key observations of the limitations and challenges in today's blockchain approaches. So first, a blockchain platform essentially provides three main functionalities: consensus, storage, and compute. Unfortunately, in most of today's blockchain platforms, all the three functionalities are coupled together, and hence makes it really difficult to scale. And also here, consensus is the slow operation, and it's often the key bottleneck. And when we do sharding, coordination also is expensive and can limit the scalability as well. So based on these observations and to address these challenges, we propose a new blockchain architecture for what we call separating execution from consensus, where we actually decouple these different functionalities of a blockchain platform, where we separate out the consensus layer, the storage layer, and the compute layer. Where the compute layer executes the smart contracts, and the storage layer persists the state, and the consensus layer agrees on the state transitions. So I think there's limited time, so I probably won't have time to go into the details here. So essentially, to separate execution from consensus, we, so again, the compute layer does the computation, and in this case, actually the compute nodes are stateless, so no consensus protocols are necessary, and they can optimistically execute the transactions. And in this case, the failures have no effect on the state. And the states are persisted to the storage layer, where the blocks are persisted and replicated. And again, no consensus protocols are necessary, and writes in this case are idempotent. And finally, the state transitions are committed to the consensus layer, and here we use verifiable computation to verify the correctness of the computation, and the consensus layer essentially tracks the state's transitions and the transaction ordering. And we use different types of techniques for verifiable computing, including majority votes and a new approach that we developed on discrepancy detection, and we can also use other methods such as zero-knowledge proofs for verifiable computing. So putting all these technologies together, we enable privacy-preserving smart contracts at scale. And here's one of the applications that we have been building together with other collaborators from ETH and doctors from Stanford, as well as DApp developers, on an application called Kara, a privacy-preserving tokenized data market for medical data. So medical data is locked in data silos, and the goal of Kara is to incentivize doctors and patients to share data and improve medical research. And we want to provide an easy, fast, and secure way for doctors and patients to essentially upload their data to the platform and share their data, and they can earn rewards for it, while at the same time preserving their privacy. And by utilizing the privacy-preserving smart contracts on top of the Oasis blockchain, the medical researchers can write their privacy-preserving smart contract, and within the smart contract, it can contain code for training machine learning models as well as serving machine learning models. And also the smart contract can specify terms of use. For example, how users may get compensated for contributing their data to the smart contract. And also, users and patients, they can also specify their own privacy requirements for their data. And if they agree to the terms of use of the smart contract developed by the medical researchers, then they can contribute their data to the smart contract developed by the medical researcher. Once the smart contract collects enough data, then it can train machine learning models over the data, and then this way can help medical researchers and pharmaceutical companies to do their medical research and to help find better cures for diseases. With this approach, it can significantly reduce the friction for medical researchers and pharmaceutical companies to get access to data to be able to train machine learning models for their work. And this is just one of many examples for the different use cases that a blockchain platform like this can enable by providing both privacy protection as well as scalability. And we just launched Oasis Labs recently. We raised $45 million, and we have a lot to build. We actually also have launched our private testnet, and we are inviting developers to join our private testnet to build applications and new technologies on top of our platform. So at Oasis Labs, we are building a privacy-first, high-performance cloud computing platform on blockchain. A new computing paradigm and computing platform that has a unique combination of set of properties, privacy, protection, scalability, as well as without needing to rely on any central party. And we hope that this technology can really help enable completely new types of applications to be built that couldn't be built today. And for more information, you can go to the website. Thank you. Questions?
Hi, I'm going back to your original example, right? The original example is there were two banks, and you wanted to build sort of a machine learning model that combined the data sets, right?
And multiple banks.
Yeah, multiple banks. So my question is, can't you solve this problem by just using secure hardware? What is the blockchain connection? It seems like you're unioning data sets, so just encrypt the data, register keys in secure hardware, and maybe run a R program inside hardware.
Right.
So what is the blockchain connection? Are you afraid of someone tampering the data? Why do you need blockchains?
Right, so usually when you use blockchain is that you don't want to rely on any central party. So then you don't need to say like who is operating this. So essentially you have a blockchain platform that people don't even need to agree on like who should be trusted or who should be operating this. So it's just a platform that without relying on any central party. And in particular, in this case, like here, I just gave an example of a few banks, but you can imagine that in other scenarios, you can have many parties, and you are not going to have all of them to agree to reach agreements on like who they want to trust, who should be coordinating and running on these things. So with the blockchain, it just helps to again, removing the reliance on any
Another question but the smart contract code itself that you register in the blockchain, that will still be public, right? That is not encrypted, right?
So that's a very good question. So in our platform, actually, this will be a choice of the developers. So the developer can specify either they want their smart contract to be public or they can be fully private. Yeah, in which case it will be encrypted.
So there's also this company, Enigma from MIT, and I was reading their white paper, and it seems like they were also trying to solve something very similar. So maybe if you could say something comparing the two approaches, that would be very helpful.
So I think for privacy-preserving smart contracts, in general, people understand its importance. So I think actually, I think it's a very good problem for many people to solve. And I think it would be great to see the whole community come together to work on this problem and solve this problem. So our academic paper is the first paper in the community that came out that actually developed technology on this. And again, I think it's a very important problem. We want to, we encourage the whole community to actually work on this.
I had one follow-up question. So in one of your earlier slides, you had approaches, right? You were using secure hardware, using multi-party computation, you were using zero-knowledge proofs, and potentially others. So my question is, like, let's assume that secure hardware is really secure. I know there are issues with that. Like, why do you need the other approaches? Because won't you be able to solve, like, say, multi-party computation if you had a secure enclave?
Okay. Yes, that's a very good question. So essentially, one of the main goals of the Oasis platform with this privacy-preserving smart contract primitive is that we want to offer, to make it easier for application developers to use state-of-the-art security and privacy technologies without needing to be an expert. And also, in this case, essentially, we provide a unified secure computing framework to leverage a combination of these different technologies. And yes, if you really just fully trust the secure hardware, then essentially you don't need to use the other, like the crypto-based techniques. But however, depending on the actual use case and also depending on developers' preference, so some developers, they just want to use crypto-based techniques. And if their application logic is simple enough, and they don't care too much about the performance overheads, then we are happy to offer them the choice of not relying on secure hardware.
Any other questions? Oh, okay, so let's thank the speaker again. Thanks, everybody. Yeah.